Hello everyone! Welcome to the Vector Database with Pinecone course. I'm eager to explore this exciting topic of vector solutions for businesses, which has gained popularity recently and is becoming increasingly more relevant. First though, let me introduce myself. My name is Ellie. I'm a course creator and head of the data content team here at 365. My background is in bioinformatics, where I was introduced to data science through courses in machine learning and statistical analysis. Additionally, I've authored such courses as 365's Machine Learning with Support Vector Machines, Data Visualization, Customer Churn Analysis, and most recently, ChatGPT for Data Science. I'm thrilled to explore new technology and trends in machine learning, especially vector databases. In the following hours, I'll introduce you to the main theoretical concepts of vector databases, vector space, and search algorithms. Our course, however, won't be purely theoretical. The second part is dedicated to working with Python and Pinecone, a significant player in vector solutions. We'll explore the Pinecone site and learn the basics of creating, deleting, and managing indexes using Python and Jupyter Notebook. The course's final section focuses on a case study using 365 company data to develop a semantic search tool for data science courses. Semantic search is a clever way to find similarities between texts based on meaning, rather than relying only on an exact match. Due to the properties, which we'll explore later, vector databases are ideally suited for providing a semantic search solution for your data. Furthermore, you could employ this not only for text, but also for images, videos, and even for audio and music searches. A music streaming service can enhance user experience by providing personalized music recommendations based on a semantic search. Aside from collecting song information about a song's genre, tempo, and instruments, you could also gather user information about listening habits, what songs are skipped, listened to, added to playlists, and so on. Then, the streaming service can offer song matches based on deeper audio characteristics and user preferences. For instance, if a user frequently listens to upbeat, energetic electronic dance music, the service can recommend new tracks with similar audio features, even if those tracks are from less-known artists or are not tagged explicitly in that genre. Beyond semantic search, vector databases are used for recommendation systems, fraud detection, customer support automation, and more, and they're only growing in popularity. I'm excited to take you on this journey, during which you'll learn about the inner workings of a vector database in theory and practice. Join me in the next lesson, where we compare traditional database solutions and vector databases. See you there! Welcome back. In this lesson, we'll compare today's leading database solutions, SQL, NoSQL, and Vector. Each has unique capabilities and serves different needs with the data ecosystem. Let's start with relational databases, or SQL databases. SQL databases rely on structured query language for defining and manipulating data. These databases are characterized by their table-based structure, where data is organized into rows and columns. Each table representing an entity has a fixed schema that enforces data integrity and relationships through keys and constraints. Picture a bank where every vault is meticulously organized and each transaction is precisely recorded. That's the essence of SQL databases. These are the traditional guardians of data, with each piece of information neatly tucked into its designated place within structured tables. They meticulously track every penny in transactions going in or out, ensuring all details are accurate. Financial institutions, retail chains, and anyone needing a ledger that stands the test of time can rely on SQL databases. To sum up, SQL databases excel in transactions, complex queries, and maintaining data accuracy, but their schema's rigidity and scalability can limit them. So, can NoSQL solutions help us combat some of these issues? Interestingly, that's precisely how NoSQL databases originated. Even though they technically existed since the 1960s, the term NoSQL wasn't introduced until the late 90s and started gathering speed in the early 2010s. NoSQL solutions then emerged as a response to the limitations of traditional databases, particularly regarding scale and agility. NoSQL is schemaless, offering more flexibility in data storage and often providing horizontal scaling solutions. They encompass various data models, including document stores, key value stores, wide column stores, and graph databases. They're optimal for large data sets with no fixed structure, rapid development, and applications where data requirements frequently change. Envision a social media giant where billions of interactions, shares, and likes surge through the digital ecosystem every minute. These modern-day titans, like Meta and Netflix, turn to agile and flexible NoSQL solutions to navigate the constant influx of real-time data. NoSQL databases, unencumbered by rigid structures, thrive on variety and volume. This allows these platforms to adapt to the ever-changing tide of user-generated content and personalized streams that traditional SQL databases could hardly keep pace with. Finally, we come to vector databases, the new frontier in data management designed to handle the complexity of high-dimensional vector space. These vectors are numeric representations of complex data, such as images, text, or sound, often generated by machine learning models to capture deep insights into the data. Vector databases allow for efficient storage, indexing, and most notably, similarity searches within this space, operations essential for machine learning and AI applications. They enable functionalities like recommendation systems, semantic search, and anomaly detection by quickly finding the most similar data points based on vector proximity. Let's step into the cutting-edge lab of a tech startup, where artificial intelligence breathes life into raw data. Here lies the domain of vector databases, the latest breakthrough in making sense of complex multi-dimensional data. They store and manage numerical vectors, the language that AI understands best. Whether it's recognizing faces in a crowd or predicting the next big trend, these databases are like brilliant minds interpreting abstract concepts and translating them into actionable insights for dynamic AI applications. As we compare these three pillars of the database world, think of SQL as the meticulous librarians, NoSQL as the dynamic storytellers, and vector databases as the visionary futurists. Each holds a unique and influential role in the data ecosystem. Selecting the ideal database is like casting the perfect character for a play. It must fit the narrative. SQL's precision is perfect for stories that require attention to detail and a traditional narrative structure. NoSQL offers flexibility, allowing the story to unfold in various directions with freedom and adaptability. Meanwhile, vector databases are for the tales that push boundaries, where the storyline ventures into unknown territories, harnessing AI's power to guide the plot. In our next lesson, we'll explore what vector databases are in more detail. Until then. Hi everyone! Welcome to our lesson on vector databases, where we'll explore their definition, significance, and recent surge in popularity. This high-level introduction sets the stage for our topic. As we progress through the lessons, we'll get into more technical details, but rest assured they won't be overly complex or daunting. When entering the world of vector databases, imagine yourself walking into a vast library with shelves that stretch endlessly upward to the ceiling. But instead of books, the shelves are filled with complex, multi-dimensional ideas waiting to be understood and connected. This is where vector databases work their magic, transforming these abstract concepts into accessible, searchable treasures. At its core, a vector database is not just a storage unit, but a powerful tool designed to manage and search through high-dimensional data. This data often comes from sources like natural language texts, images, and audio, all of which are transformed into numerical vectors. Think of a vector as a pointed arrow in a vast multi-dimensional space. Each dimension in that space represents a feature which you can consider a characteristic of the data. For instance, in a music app, vectors could represent different aspects of a song, its rhythm, melody, instruments used, and even the emotions it evokes. Similarly, vectors could encapsulate each image's colors, shapes, and textures in a photo app. And since vectors are objects in space, we can measure the distance or similarity between each two vectors when we have multiple vectors. This will be a central concept that we'll explore later. But for now, let's focus on what vector databases have been used for in recent years. Vector databases shine in scenarios where traditional and NoSQL databases falter, most notably in similarity search. Imagine using a fashion app and uploading a picture of a dress you like. A vector database can quickly sift through thousands of products to find similar dresses in color, style, fabric, and design. This capability stems from their ability to understand the distance between vectors, where closer distances mean more similarity. This is only one of many possible applications for vector databases. In healthcare, they can help clinicians find similar case studies or medical images, aiding in diagnosis and treatment. In customer service, they can match queries with the most relevant answers by understanding the essence of questions and historical data. So when were vector databases first introduced? They originated in the early 2000s, when California researchers began developing a database to store and query high-dimensional vectors. The first commercially available database was released by VectorWise in 2010. But these solutions really found their purpose in the growing data volumes of businesses and the increasing importance of customer recommendation engines. In the practical part of our course, we'll explore the Pinecone databases, developed by a former Amazon employee who devised a vector solution to address the challenges of searching for similar items within a large consumer base. You could say that the growth in daily business data volumes, coupled with the limitations of traditional and NoSQL databases in managing similarity searches, has paved the way for vector databases. As we venture deeper into the digital age, the relevance of vector databases will only increase. They are poised to revolutionize industries by enabling smarter search engines, more personalized recommendations, and even advancements in autonomous technologies. In our following lessons, we'll explore how these databases work, examine key players like Pinecone, Milvus, and Weaviate, and see how they're applied in real-world scenarios. By the end of this course, you'll understand vector databases and be ready to harness their potential in your own projects. Next up, it's time to step into the world of vector spaces, the pillar on which a vector database is built. Can't wait to see you there! Welcome to this introductory lesson on vector spaces. As we embark on this journey, think of yourself as an explorer venturing into a new universe. A universe not bound by the familiar 3 dimensions of our everyday world, but one that extends far beyond, into realms that can only be navigated with the compass of mathematics and the map of intuition. In the heart of every vector database lies the concept of a vector space. But what is a vector space? Simply put, a vector space is an abstract mathematical structure where vectors reside. These vectors are not just arrows pointing from one place to another. In the context of vector databases, they're also carriers of information, each dimension representing a different feature or characteristic of the data. Imagine walking into a gallery where each painting is not just a flat image, but a portal to a world with many dimensions. Some dimensions represent the colors used, others the brushstrokes, and still others the emotions the painting evokes. Each piece of data is like one of these paintings in a vector space, only it is described by its unique set of dimensions. Mathematically, a vector space is a set whose elements, also known as vectors, can be added together or multiplied by numbers. We can exploit those properties when working with a vector database. Vector space is the foundation upon which the magic of similarity search is built. When we search for something similar in a vector database, we look for similarity in this multi-dimensional space. The closer the 2 vectors are, the more similar the data they represent. With that in mind, let's explore how a vector database is created using our gallery of paintings as an example. In this gallery, each painting is not just an image, but a complex amalgamation of various features captured in the multi-dimensional space of a vector database. These features can include the painting's name, the epoch or period it belongs to, its style and technique, its size, and even its current location. Each of these characteristics contributes to defining the position of the painting within the vector space. For instance, Leonardo da Vinci's Mona Lisa is not just a portrait of a woman, but a masterpiece from the Renaissance, characterized by specific painting techniques and an emotional depth that resonates through the ages. Nearby, you might find The Lady with an Ermine, another of da Vinci's works, sharing many features such as the artist's unique style, the era, and the emotive expression, positioning it closer to the Mona Lisa within the vector space. Similarly, Johannes Vermeer's The Girl with a Pearl Earring, while also a portrait of a woman, sits in a slightly different part of the vector space. It shares the portrait style and the emotion evoked, still differences in the artist's technique, the Dutch Golden Age's distinct epoch, and other features like the lighting and color palette set it apart. Yet it remains relatively close to Da Vinci's works because of the overarching similarities in subject and form. Observing the paintings, we can see the similarities and differences, such as the different styles. The Dutch painting is from a different era and style and has a more contemporary close frame. The key here is to capture all this information, the style, artist, name, and technique, and encode them into numerical vectors. This could involve straightforward encoding, like assigning numbers to different artists, or more complex feature extraction, like analyzing the color spectrum used in the painting. We can enable powerful similarity searches when we populate our vector database with these encoded paintings. For example, a query for Renaissance portraits could quickly surface works by Da Vinci, Michelangelo, and Raphael clustered together due to shared features in style, epoch, and technique. On the other hand, a search for portraits of women could span wider, pulling in works from different periods and artists, but similar in subject and form. In this way, vector databases transform our understanding and interaction with data, opening new dimensions of discovery and insight in fields ranging from art history to digital media, marketing, and beyond. That sounds good in theory. However, we still need to answer a crucial question. How do we measure similarity? For that, we'll need to be aware of distance metrics in vector space, and that's precisely what we'll talk about next time. See you there. Thanks for watching. Welcome to the lesson on distance metrics in vector space. Today we'll examine the heart of how we measure the closeness and similarity between data points. We've already discussed that a vector space has certain properties, such as adding, multiplying, and scaling a vector. Today we'll discuss how we measure the distance between vectors. Our main topic for this lesson concerns different distance metrics. These metrics originate from linear algebra, but find practical application when building a vector database. In the world of vector databases, distance metrics helps us determine how close or similar data points are to each other within the vector space. And it turns out there is a different way you can measure that closeness depending on what metric you use. Let's start with the first one, Euclidean distance, probably the most common metric. This metric measures the straight line distance between 2 points in space. It's akin to using a ruler to measure the distance between 2 dots on paper in a two-dimensional space. Mathematically, for points P and Q in an n-dimensional space, the Euclidean distance is defined as the square root of the sum of the squared differences of the 2 points. This metric is particularly useful for applications where the actual physical distance is important, like spatial navigation or clustering. Okay, what's next? Another popular metric is the Manhattan distance, also known as the city block or taxicab distance. It takes its name from the famous Manhattan grid where cars or cabs must travel along similar lines. Manhattan distance measures the distance between 2 points when you can only travel along orthogonal right-angle paths. For points P and Q, it's calculated as the sum of the absolute differences of their Cartesian coordinates. This distance is particularly relevant in urban planning simulations or scenarios where direct paths are impossible. You wouldn't be able to cut across a road diagonally with your car or go there on foot if buildings or structures were in your way. Okay. Now it gets a bit more intriguing with a metric often used in vector databases, the dot product. The dot product, also known as the scalar product or inner product, is a fundamental operation in vector mathematics and plays a significant role in vector databases, especially in the context of similarity search and machine learning. The dot product of two vectors is a measure that combines their magnitudes and the cosine of the angle between them. Mathematically, for two vectors, a and b, the dot product is calculated like so. This results in a single scalar value. The magnitude or length of a vector is the square root of the sum of each scalar squared. So for a vector s, we'd have a magnitude of 15.94. Pay attention to the fact that we're measuring the magnitude and angle between the two vectors with the dot product. So what does a dot product indicate? A positive dot product indicates that the vectors are pointed in roughly the same direction. A zero dot product signifies orthogonality, perpendicular vectors. A negative dot product shows that they are pointed in opposite directions. Incidentally, calculating the dot product is computationally efficient, making it a preferred method for high-volume, high-dimensional data processing in vector databases. This efficiency is critical for real-time applications like search engines and recommendation systems where quick similarity assessments are needed. This equation is also important because it leads us to our lesson's final concept, cosine similarity. If we rearrange the terms in the dot product equation, we'll arrive at the cosine between two angles because their dot product is divided by their magnitude. The cosine similarity is linked to the dot product. The difference is that rather than measuring distance, cosine similarity evaluates the cosine of the angle between two vectors. So crucially here, we're not only measuring the distance between 2 points, we're actually looking at two vectors. And what do vectors possess? Yes, a direction. So if two vectors have different directions, their similarity will be higher. This measure goes from 0 to 1. So in this example, we have only 2 dimensions, and we have the following words: clever, dandelion, and flower. We'll see that the direction of the dandelion and flower tends to be the same because they belong to the same category, flower or floral. That's why their score would be close to 1. So to sum up, this approach is less about the literal distance and more about orientation and direction. It's a key metric in text analysis and recommendation systems where the importance lies in the direction or context rather than the magnitude of the vectors. These metrics allow us to perform efficient and meaningful similarity searches in vector databases. For instance, when a user uploads an image to a search engine to find similar ones, the engine uses these metrics to compare the user's image vector with vectors in the database, rapidly identifying those with the smallest distances or highest similarities. By mastering these distance metrics, we gain the power to navigate vector spaces with precision, tailoring our approaches to the specific needs of each application. Whether grouping similar items, recommending products, or identifying patterns, these metrics are the way we can measure how similar they are. All right, great work, everyone. We have just one more math-focused lesson on vector embeddings. But don't worry, you'll see that the embedding process isn't quite as complicated as it may sound at first. See you there. Hi again. Today we'll unpack the embedding process step by step. This is a pivotal concept in modern natural language processing, NLP, and machine learning, ML, because it allows us to transform raw data into the structured, machine-understandable format of vectors. Ready? Let's dive in. First, let's define what we mean by embeddings. In the simplest terms, embeddings are dense representations of data items, such as words, products, or users, in a continuous vector space. Each vector dimension captures some aspect of the data item, allowing similar items to be placed closer together in the vector space. Why do we need embeddings? Well, we need embeddings because computers don't do well with words, but they're excellent with numbers. So during the embedding process, we take words and create an array with numbers representing different characteristics of the word. Let's look at an example. He plays the lead guitar in a band. They found high levels of lead in the drinking water. These sentences show that the same word is used in different contexts. So how would we embed these sentences? For simplicity, let's say that each vector will have only 2 dimensions. But remember that in practice, we'd typically have at least 300 dimensions, generally over 1,000. Let's assume that the first dimension captures relevance to musical contexts, and the second dimension captures relevance to substance-related contexts. Let's start with the first sentence. He plays the lead guitar in a band. For this musical context, let's assign vectors with relatively higher scores in the first dimension and lower scores in the second. Now, he is a pronoun irrelevant to either domain, which results in low scores for both dimensions. The second word plays is strongly associated with action, especially in a musical context, and is therefore high in the first dimension. As an article, The has low relevance to specific contexts. That's why it gets low scores. Which brings us to lead, which in a musical context refers to a primary role and consequently earns a high score in the first dimension. Guitar is entirely musical, receiving the highest score in the first dimension. In is a preposition with generic usage, so it has low scores, and a is an article like the. Finally, band strongly signifies a group of musicians, therefore gets a high score in the first dimension. So far, so good. Then what about the second sentence? They found high levels of lead in the drinking water. For this substance-related context, we would assign vectors with relatively lower scores in the first dimension and higher scores in the second. Starting with they, which is a pronoun, mostly context neutral. That's followed by found, which implies discovery, relevant more to the substance context here. High is contextually more related to quantity or degree in substance. In the same way levels, in this context, points to measurement, highly relevant to substances. Of, on the other hand, is a preposition, low relevance but slightly more towards substance due to its frequent usage in descriptions. Lead here refers to the metal, highly relevant in the second dimension. The next two, in and the, remain generic. What about drinking then? Drinking ties directly to the use of water, therefore higher in the second dimension. Speaking of water, this is a substance, scoring high in the second dimension. And there you have it. So even though we have the word lead twice in our vector database, it carries a different meaning. That's why its vector representation in the sentence is completely different. And that's, in effect, how an embedding algorithm works. All right, everyone. With that cleared up, we're ready to start coding. In the next section, we'll explore Pinecone and use Python to connect to the Pinecone server. See you there!